In this lesson, I'd like to introduce you to logarithmic functions. So as we get started, let me remind you of the exponential function f of x equals 2 to the x, which we studied in the previous lesson. The graph of that function looks something like this. Now, here's an interesting thought. I want to add to that graph the graph of the line y equals x. So I throw that into the mix as well on the same set of axes. And now, here's my question to you. Where would the graph of the inverse function of 2 to the x live on that same set of axes? Is it easy to see where it would be? And remember, the graph of an inverse function has to be the mirror image of the graph of the original function about the line y equals x. And that's exactly why I drew that line y equals x into this graph. Now, that's where the inverse would have to be, but where would it be in this particular example? Well, to draw this inverse function of the graph of 2 to the x, we would have to start down by the bottom of the y-axis and draw a curve which stays in the fourth quadrant and stays pretty close to the y-axis until it crosses the x-axis, and then it would have to turn away from the line y equals x and travel through the first quadrant in a somewhat flat-looking way. And now it turns out that that graph that we just drew is pretty straightforward to understand if you know what a logarithm is. So in this lesson, I'm going to define what logarithmic functions are, I'm going to study some of their properties, and we'll look at their graphs. In fact, this last graph we just drew would be the graph of a logarithmic function. So, to get us started with some of the mathematics, let's look at the definition of a logarithm. The logarithm to the base b of a positive number y is denoted by log subscript by and is defined this way. If y is b to the x power, then the log base b of y equals x. So, for example, since I know that 3 to the power 2 equals 9, I also know that log base 3 of 9 equals 2. Do you see how the input and output values sort of change roles? When I look at something like 3 to the second, I'm thinking of 3 to the x and plugging 2 in and getting 9 back. But if I have this function now, log base 3 of x, and I plug 9 in, I get the 2 to come out. So the idea here is that the inputs and the outputs have changed roles. Now, I have to tell you that exactly what we just did between this 3 to the 2 and the log base 3 is exactly what you do when you define inverse functions. So this idea of switching back and forth between b to the x and log base b is exactly what we understand when we talk about these inverse functions. In some sense, the logarithmic functions undo what the exponential functions do, and vice versa. And that's why we call them inverses of one another. So, for example, log base 2 of 8 equals 3. And the reason that's true is because 2 to the 3 equals 8. And that's exactly how you want to calculate something like log base 2 of 8. You have to think backwards about the function 2 to the x and ask yourself, what number x would I plug in to get 8 back? And that's where the 3 comes from, because 2 to the 3 is equal to 8. So this backwards thinking, so to speak, between exponential functions and logarithmic functions has to come natural to us now. We have to get used to doing this sort of thing so that we can find these values of logarithms. Now, I'd like us to then think about evaluating one of these logarithms ourselves by looking at the following example. Evaluate log base 3 of 81. In other words, I want you to tell me what the number log base 3 of 81 equals. Well, this question is really asking us to find a value, I'll call it x, so that 3 to the x equals 81. And honestly, I think you should always translate these kinds of logarithm problems into a new exponential problem like I just did. So I'm now looking at 3 to the x equals 81, and I'm asking, what number should I plug in for x to make that true? Well, the answer is 3 to the 4, right? I should plug in a 4 because 3 to the 4 is 3 times 3 times 3 times 3, and that's 81. So that 4 is what I need to solve the original log problem. In other words, log base 3 of 81 equals 4. So the final answer there is actually 4. Now, just to get a bit of practice, let's do another one of these. Now, these numbers don't always work out perfectly. In fact, they often work out to be a bit messy. But let's try another example where the number doesn't work out amazingly well, but it works out pretty well. Evaluate log base 4 of 32. Now, just like when the example I just did with you earlier, I want us to ask ourselves this question. What value of x do I need so that 4 to the x power gives me 32? Well, I don't know about you, but I can't quickly do that. I don't know a specific whole number to plug in for x so that 4 to the x equals 32. But I know how to manipulate that equation enough to get the value of x. Here's how. Start with 4 to the x equals 32 and rewrite it as 2 to the 2 to the x equals 32. And of course, 32 is 2 to the 5th. So what you really have is 2 to the 2 to the x equals 2 to the 5th. Now, 2 to the 2 to the x can also be written as 2 to the 2x. That's one of the laws of exponents. So what you really have is 2 to the 2x equals 2 to the 5th. Now, here's an important fact that we've used before in these kinds of exponential problems. If you have two quantities that are equal, like we have here, 2 to the 2x equals 2 to the 5th, and the bases are equal, notice that we have 2's on both sides as the bases, then the exponents have to be the same. And that means I can conclude then that the 2x, which is the exponent on the left, has to equal the 5, which is the exponent on the right. Well, 2x equals 5. You and I could solve that pretty much in our sleep, probably, because now we just divide by 2, and we have x equals 5 halves. So my original problem, finding log base 4 of 32, I now know the answer. That's equal to 5 halves. All right, with these examples done, let's move forward to thinking about logarithmic functions at this point. And think about a little bit related to their graphs, for example. Notice that the two examples we just did were not functions because there were no variables floating around. When I said find log base 3 of 81, there were no x's there. So now I want to think of these things as functions, though, and see where we go from there. First off, from the graph I showed you at the beginning of this lesson, we know that we need to think carefully about the domain of a logarithmic function. Did you notice that that last graph we drew, the one that started way down at the bottom of the y-axis and worked its way across the first quadrant, that graph was completely on the right-hand side of the y-axis. There was no part of that graph that was on the left side of the y-axis. Now there's a reason for that, and it goes back to the domain. The domain of a logarithmic function of the form y equals log base b of x is always just the set of positive real numbers 0 to infinity. And I want to make a very important point here. The 0 is not included in that domain. So the domain of a logarithmic function, log base b of x, is always just the set of positive real numbers. Now, why? Why is that true? Well, think about it for just a second. If you wanted to plug in a negative value into a logarithmic function, let's say you had the function log base 2 of x, and you plugged in negative 64. So you were asking me now to find the log base 2 of negative 64. You would be saying that you were asking me to find a value y so that 2 to the y equals negative 64. But no matter what you plug in for y, you're never going to get 2 to the y to be negative. It'll always be some positive number. It might be some very large positive number, or it might be some very small positive number, but 2 to the y, no matter what you plug in for y, will be positive. So you simply can't plug negative 64 into a logarithmic function like log base 2 of x. Okay, so the domain of any of these logarithmic functions has to be just the set of positive real numbers. What about the range of one of these functions? Well, that's a good question to ask. It's pretty clear, again, just from that picture that I showed you at the beginning of the lesson, that the range must go down to minus infinity. So when you're looking in the y direction to talk about the range, the downward path of that graph tells me it's going to go to negative infinity. By the way, the graph of y equals log base b of x never touches that y-axis. And it never touches the y-axis for the reason that its corresponding exponential function never touches the x-axis. Remember, these two graphs, the exponential function graph and the logarithmic function graph, need to be mirror images of one another. So this log base b of x graph never touches that y-axis. But what about the other part of the range, the part that seems to come up into that first quadrant? What's happening there? Does it flatten out and lie underneath a horizontal asymptote, or does it grow forever even if it's slow? Well, the answer is that it does grow forever, and it keeps growing up, 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 but it does it very slowly. So the range of one of these graphs is actually the set of all real numbers. They go down as far as you want, and they go up as far as you want as well. Now, so what do the graphs really look like? Especially if you start changing the base of the logarithmic function, the log base b. What does that graph look like as b changes from, say, 2, 3, 4, and so on? The best way for us to answer these kinds of questions is to sketch the graphs of these functions, plot some points, connect the dots, and see what we get. So let's walk through an example of doing this sort of thing and see if we can really get a feeling for why these logarithmic functions have graphs with these shapes. Let's sketch the graph of f of x equals log base 3 of x. Well, let's be really honest. There are going to be some nice values of x to plug in, and there are going to be some really not so nice values of x to plug in. And as I've said to you in previous lessons, when we do this kind of activity, we should choose some intelligent values of x to plug in so that the function's y values are easy to find. In this case, the smart values of x that you and I should plug in are the powers of 3. And we're going to choose powers of 3 because the base of this logarithmic function is 3. So I'm going to plug in things like 1, 3, 9, 27, and 81 because I can find the log base 3 of those values quickly. So let's do that now. F of 1, which would be log base 3 of 1, would be the number that we would raise 3 to get 1. So what do you have to raise 3 to in order to get 1? Well, that answer is 0. Since 3 to the 0 is 1, I know that the log base 3 of 1 is 0. Remember, you have to kind of think backwards between the logarithmic function and the exponential function. So f of 1 is 0. What about f of 3? Log base 3 of 3. Okay, that's the number that you would raise 3 to get 3 back. Well, that answer then is 1 because 3 to the 1 is 3. So f of 3 is 1. Similarly, f of 9, which is the log base 3 of 9, would equal 2 because 3 to the 2 equals 9. You getting the hang of this? This is the idea behind how to find logarithmic values. What's f of 27? Well, it's log base 3 of 27, and that would be 3 because 3 to the third power gives me 27. And lastly, f of 81 would be 4 because log base 3 of 81 is 4 because 3 to the fourth is 81. Now, you could plot these points and you could start to sketch out the graph. And let me make a few comments about that graph as we go from here. First of all, notice that you know the x-intercept thanks to the information we found. The x-intercept is at 1, 0. You also notice, if you sketch a few more points and work your way through, that you'll have a vertical asymptote at the line x equals 0. Now to see that, you would have had to plug in some other values of x, maybe some smaller ones that are still positive, like 1/3, 1/9, 1/27, 1 over 81, and so on. Again, choosing those denominators to be powers of 3. You might also notice that this graph, log base 3 of x, has the same shape as the graph of log base 2 of x, which is the one that I had us graph at the very beginning of the lesson. So the next question we really should ask is, how do these graphs compare? Well, let's plot them on the same set of axes along with something like y equals log base 7 of x, let's say, just to see if we can see some of those differences between the graphs. Well, what do you see? Well, first of all, in that little region between x equals 0 and x equals 1, the logarithmic function which is above the others is the one with the larger base. In other words, the log base 7 of x in this example. But once x gets bigger than 1, the function that function takes on the role of being the smallest compared to the others. And so, in other words, log base 7 of x, once x is bigger than 1, is actually the one that's the lowest or the smallest. And in that part of the domain from x greater than 1, the function which is actually the highest is the log base 2 of x. Now, this can be kind of counterintuitive at first because you want the one with the larger number to be the larger function. In this case, though, log base 2, which actually has the smallest base in the example, is actually above or larger log base 7 of x, which has a larger base. So you may have to work your way through some of that possibly confusing information as you're working through which graph is above and which graph is below. Now, just as with other kinds of graphs that we've seen in the past, we can play the usual games of shifting them upwards or downwards, left and right. I'm going to pass on that for now because we have lots of other things to talk about today with logarithms, but you may want to get used to thinking about how you would shift the graphs of these basic logarithmic functions, either left and right or up or down. Now, let's transition to a discussion of some properties of logarithms now, which really do cause some students a bit of trouble. So you're going to want to really put these to memory and remember them bit by bit and remember them exactly because it's easy to mess them up, to confuse them. So we're going to talk now about these properties of logarithms, and there are three main ones. So let me quote them to you here. We're going to let capital M, capital N, and B be positive numbers, and B is not going to be 1. And we're going to let x be any real number. Then here are the three properties of logarithms that you want to keep in mind. First, log base b of m times n equals log base b of m plus log base b of n. So you go from a multiplication on the inside of the logarithm function, m times n, to two separate logarithms which are combined by an addition. Can you see why some folks get confused with these properties? So that's the first property. The second property is that log base b of m divided by n is the same as log base b of m minus log base b of n. And the third property says that if you take the log base b of m raised to the x power, so you've plugged m to the x into the function, it's the same as x times log base b of m. In other words, that nice exponent that's on the m, that's inside the function, is actually allowed to come out in front and become a multiplier next to the log. So log base b of m to the x equals x times log base b of m. If I put numbers in, for example, I might be saying that log base b of 3 squared is the same as 2 times log base b of 3. Now, these properties are really useful when you're trying to simplify expressions that involve logarithms. So I'd like to spend a few moments looking at some examples where we combine values of logarithms using these properties. So let's look at this one together. Write the log base 3 of 162 minus the log base 3 of 18 as one logarithm and simplify as much as you can. So the idea here is to take that difference of two logs and actually try to write it as one logarithm. Well, if you look at the second property I quoted a moment ago, the right-hand side of that property has log of something minus log of something else, and that property is the one we're going to want to use here. So log base 3 of 162 minus log base 3 of 18 is the same as log base 3 of 162 divided by 18. So that's the second property I shared with you earlier. And now I can simplify 162 divided by 18. That's just 9, if you just do some long division or however you want to work through that actually. And log base 3 of 9, we can simplify that even further because I know that 3 to the second power equals 9. So the log base 3 of 9 is equal to 2. So that really unenjoyable looking expression we started with, log base 3 of 162 minus log base 3 of 18, is actually just a really fancy way of writing the number 2. Now, let's try another example, and you might want to try this one on your own first just to see if the laws of logarithms, or these properties of logarithms, if you will, are making sense as you try to do this example. Write 2 times log base 5 of x plus log base 5 of y minus 3 times the log base 5 of z as a single logarithm. And just as a hint, you're actually going to need all 3 properties I mentioned earlier in order to do this. And those were log base b of m times n equals log base b of m plus log base b of n, and log base b of m over n equals log base b of m minus log base b of n, and lastly, log base b of m to the x equals x times the log base b of m. Now, as we walk through this example, I do need to stress one important thing. Notice that all the terms that we started with are log base 5. Did you see how they were all log base 5 of something? If those bases were different, let's say the first term had a log base 5 and the other one had a log base 6 in it, then none of this would work. So the fact that those are all log base 5s is crucial to finishing this example. Now, as you look at the first term, which was 2 log base 5 of x, that's 2 times the log base 5 of x, we were reminded of the third property, which says that I can rewrite that as log base 5 of x squared. You see how that 2, which was in the exponent of that x squared, can be brought out in front. It can also be pulled back inside, if you will. So 2 times the log base 5 of x is the same as log base 5 of x squared. And so now I can walk my way through that third term that has a 3 in front, and I can actually rewrite that as well. Instead of 3 log base 5 of z, it's the same as log base 5 of z to the third power. So now let's use these properties and finish this up. The first 2 terms now are log base 5 of x squared plus log base 5 of y. Those can be combined using the first property to give me log base 5 of x squared times y. And now I have log base 5 of x squared times y minus log base 5 of z cubed. Remember, I pulled that 3 back up into the exponent inside the z. And now the second property says I know how to combine when I have a minus sign between the two. And when I have a minus sign, that log base 5 of x squared y minus log base 5 of z cubed becomes log base 5 of x squared times y divided by z cubed. And notice the x squared and the y divided by the z cubed are now all inside the log base 5 function. Well, that was my goal, was to write that complicated looking expression as one logarithm. So we accomplished that, and that's very well done. But believe it or not, the big reason to actually use these logarithms is usually not to put a whole bunch of logarithms back together. It's actually to split one complicated looking logarithm apart into smaller pieces. That's actually why logarithms were developed in the first place. So let's do another example where I try to show you how you can take the log of a very large number and split it into smaller pieces with the goal of finding the log of the big number. Given that log base 4 of 2 equals 1/2, and log base 4 of 3 is about 0.7925, I want us to determine the value of log base 4 of 60,466,176. Now, I'm going to start out and being really honest with you. I'm willing to admit that I carefully selected that 60,466,176. But I really want to illustrate this point, so that number is carefully selected, but it'll still make the point, I think. Let's start factoring 60,466,176, realizing that a lot of 2's and a lot of 3's are going to come out as I start to factor. As you do that and you keep pulling 2's and 3's out of that number, you'll find after a while that that number, 60 million and so on, is just 6 raised to the 10th power, okay? So what I've really asked you for then is a logarithm of 6 to the 10. But now that reminds me of the third property of logarithms. When I have an exponent, I'm allowed to actually pull that exponent out. So let's keep going now as we work through the steps of finding this logarithm. So this log, which was log base 4 of 60,466,176, is actually just equal to log base 4 of 6 to the 10th power. Now that's in some sense the hard part of the problem, to realize that the number inside those parentheses was just 6 to the 10th. But now I can attack this with the properties of logarithms. First of all, the 10 can be pulled out in front. And all of a sudden I have 10 times log base 4 of 6. Can I point something out here? We've just converted this problem from looking at log base 4 of 60,466,176 to just finding the log base 4 of 6 and then multiplying by 10. And this is the power of these logarithms, that you can whittle a big problem down to a much smaller one. Now, that's the same as 10 times the log base 4 of 2 times 3. And we have one property that tells me how to split when I have a 2 times 3 like that, so that this becomes 10 times log base 4 of 2 plus log base 4 of 3. Notice that that 10 needs to sit out in front. It's going to have to be distributed later on if that's the way we want to do it. And now I gave you what log base 4 of 2 is. It's 0.5. And I also gave you an approximation of log base 4 of 3. It's 0.7925. So our number becomes 10 times 0.5 plus 0.7925, which is 10 times 1.2925. And of course, 10 times that is just 12.925. Now that's pretty nice. I think it's a really cool example to show us how these logarithms have these great properties that allow the calculations of very large values for logarithms to be whittled down to a problem that we can really handle. And it really was for these kinds of calculations where we would want logarithms of very large numbers to be whittled down to logarithms of very small ones. It was this reason that really motivated the definition of and the development of logarithms many years ago. Now, let's practice with one more of these kind of expand type problems, and then we'll go ahead and close out our lesson for now. I want to expand and simplify log base 8 of 8 times the square root of 7c to the 5th. Now, there's a lot here actually, so let's just walk our way through a little bit of the problem one step at a time and see how this works. First of all, log base 8 of 8 times the square root of 7c to the 5th is the same as log base 8 of 8 plus log base 8 of square root of 7c to the 5th. So I've split this up now just a little bit, and I notice first of all that I can do the log base 8 of 8 pretty quickly. That's just equal to 1 because 8 to the 1 equals 8. So I'm now down to 1 plus log base 8 of the square root of 7c to the 5th. Now, that's the same as 1 plus log base 8 of 7c to the 5th raised to the 1/2 power. That's what the square root means. And now that I have that power of 1/2, the third property allows me to pull that 1/2 and place it out in front. And that means I now have 1 plus 1/2 times the log base 8 of 7c to the 5th. Now let's keep going. The 7c to the 5th can also be split up because it's a product. And I'll have 1 plus 1/2 times the log base 8 of 7 plus log base 8 of c to the 5th. And that 1/2 has to be multiplied with both of those terms. And now I can clean this up just a little bit more. Distribute that 1/2 out, and I'll have 1 plus 1/2 log base 8 of 7 plus 5/2 log base 8 of c, because that c to the 5th allows the 5 to come out in front. It multiplies with the 1/2, and I get a 5/2. And that's the final answer. So I split up what looked like one very complicated log into 3 terms, all of which look pretty straightforward. Well, we've completed a pretty quick introduction to logarithmic functions today, as well as some exponential function material in the previous lesson. To be honest, it would take many more lessons to really do justice to exponential and logarithmic functions. We're going to cover them once more in the next lesson as we solve problems involving these types of functions. But I would strongly recommend that you study them further, especially as you look to taking pre-calculus or calculus courses in the future.